Hey guys, welcome to another math lesson by the Magic Monk. And today we're going to continue with our calculus series, and we're going to apply some of the calculus that we have learned to a real life situation in projectile motion. So we're going to explain what all that means. The first thing we want to do is talk about what projectile motion is. So let's say we have two people standing a certain distance apart from each other, and one person throws a ball or hits a ball or whatever kind of ball you play with in your country, basketball or baseball, whatever it is. They throw it at the other person. Usually the ball will travel in a parabolic shape. So in a parabolic shape down this way, and the other person then catches it with their gloves or hands or whatever, and basically the ball will reach a certain height. So let's say initially the height of the ball is 0, and what we're doing is we're looking at the vertical displacement, and which we're going to use the symbol S because that's the convention of displacement reached by the ball. Vertical displacement reached by the ball. So initially, when this person is holding the ball, S is equal to 0. Right? When the ball reaches the top, the highest point in the air, let's just make up a number here and say S is equal to 20 meters. Now I know that's a very big number, but let's just imagine this person is very strong and throws the ball really high, and then the other person catches it at this point, and S is back to 0 again, right? Because let's just assume that 0 meters is just before when the ball is thrown up. Now this is the vertical. We're looking at the vertical displacement. So we don't care about the horizontal displacement at all. We don't care how far the ball has traveled. We only care about how high, the height of the ball, or how high the ball has gone up. And the other quantity we're concerned with is time taken in seconds. So the displacement S was in meters, and obviously we're using the English spelling, even though most of our viewers are probably from America, in which case you probably wouldn't use meters anyway. But so we got meters is the vertical displacement, the units for the vertical displacement. And what I want to do is to draw a graph of the displacement of the ball against the time. So initially when this person is holding the ball, the time is 0 seconds. Right, the initial moment. And then after he throws it up and the other person catches it, at this point the time is, let's say, 4 seconds. Right? It has taken 4 seconds for this ball to travel to reach the other person. So now we're going to draw a graph of the vertical displacement, which is S, against the time T. So here is the graph that I have already drawn in GeoGebra. And the equation of this graph is f of x, x is the time, is equal to -5 bracket x minus 2 squared plus 20. Right? If you type this equation in GeoGebra, you should get this graph. And notice how I have defined a domain for x, and if you want to do that, you'll have to watch our piecewise functions tutorial on how to draw that in GeoGebra. So basically you draw this graph in GeoGebra, and I'm just going to copy this graph into my smooth draw program. And so basically we have the horizontal axis of this graph is the time, which is in seconds, and the vertical axis is the height, or the vertical displacement, which is in meters. So the equation of this graph is S is equal to -5 bracket t minus 2 squared plus 20. As you can see, at the highest point, the ball reaches 20 meters at 2 seconds. 2 seconds. And now I'm going to give you guys a question that requires your understanding about rate of change. And the question is, what is the average velocity? So remember the keyword here, average velocity of the ball from time is equal to 0 to time is equal to 2 seconds. So what is the average velocity? Now, average velocity refers to how fast is the ball traveling, and obviously we're looking only at the vertical displacement. How fast is the ball going upwards in the first 2 seconds? And when we're talking about velocity, that is the change in displacement over a fraction change in time. Because we're talking about how fast, so that is a rate of change. The rate of change of displacement with respect to time, and we can also call this change in S over change in T. Now the change in S is therefore the rise divided by the run for our 2 points where time is equal to 0 and time is equal to 2, the vertical difference or the rise divided by the horizontal difference, which is the run. Horizontally, these 2 points, the difference between these 2 points, and vertically the difference between these 2 points. Now, the rise is therefore 20 meters, and the run is 2 seconds. The change in time is 2 seconds, and therefore 20 divided by 2 is 10 meters per second, or you can also write as 10 ms to the power of -1. Now this is the average velocity, and we haven't used any calculus yet. We're using the pre-calculus principles for rate of change, and now we want to use some calculus, and we want to talk about the instantaneous velocity. or in other words, the instantaneous rate of change at, let's say, when the time is equal to 1 second. Now, what is the instantaneous velocity? Well, instantaneous velocity, if you remember, is when oh, I spelled instantaneous wrong. Instantaneous velocity is when we have still the same thing, change in s over change in t, but it's the limit of change in s over change in t as change in t approaches 0. And you probably have to go back to the calculus tutorial to understand this. But basically, the 2 points that I'm picking are so close together that their change in time, their horizontal distance is 0. And therefore, it forms a tangent line at this point when t is equal to 1 second. And we're trying to find out what the gradient of this tangent line is. And the gradient of this tangent line at time is equal to 1 is the velocity of the ball, the vertical velocity of the ball at this point. So therefore, we're looking for ds over dt, which is the symbol for the derivative of s. So ds over dt, now we're trying to differentiate this equation now. And this equation, if we have a look, just going to copy that equation because now we have to differentiate it to find out the derivative. So what I want to do is, firstly, because I haven't talked about how to differentiate equations involving brackets, I just want to expand that. So I'm going to expand this part first, and that becomes t squared plus 4 and minus 4t in the middle. And then plus 20 at the end. So now we have s equals negative 5t squared plus 20t minus 20 plus 20. Right, if you remember how to expand the bracket. If you don't know how to expand, you should go back to the expanding tutorial. So now we can cancel these two numbers out, and this is our equation for s in expanded form. And if we want to differentiate that, that becomes really easy because we can just use the rule where we bring the power to the front. So it's negative 10, 5 times 2 is 10, t, minus 1 in the power, 2 minus 1 is 1, plus 20, right, because if you bring the 1 to the front, it becomes 20 times 1, and the power is 1 minus 1, which becomes 0, and t to the power of 0 is equal to 1, so you don't write the t anymore. So that is the differentiated equation. Now, notice how we want the instantaneous velocity when t is equal to 1. So we have ds over dt is equal to negative 10 times 1 plus 20 is equal to 10 meters per second. So we can say at time is equal to 1, the speed is 10 meters per second. Right, at time is equal to 1. So if we draw a tangent line at time is equal to 1, I'm just going to see, kind of forgotten how to draw it. So we go to tangent and we draw a point. Hang on, just going to figure that out first. So I'm drawing a point A at this point, which is t equals 1. I'm going to draw the tangent line, pick the point, pick the line. Okay, and let's have a look at the equation of this tangent line. And it is approximately 10 for the gradient of the tangent line. Alright, so we have got it correct. The gradient at time is equal to 1 is 10 meters per second. So therefore, the rate of change of displacement with respect to time when t is equal to 1 second is equal to 10 meters per second. And you can do this for any points on the graph. So for example, if I want to know the instantaneous velocity when time is equal to 2.5, so I have the equation for the instantaneous velocity is negative 10t plus 20. So if we have negative 10 times 2.5 plus 20, so that's negative 25 plus 20, which is negative 5 meters per second. So what that means is at time is equal to 2.5, the gradient of this line, of the tangent line, which represents the speed or the velocity, actually not speed because we're taking into account the direction. So the velocity of the ball at time is equal to 2.5 is negative 5, as shown by the gradient of our tangent line here. Okay, so I hope you guys understand a little bit about how to find the instantaneous velocity, and we're going to talk about acceleration in the next tutorial. See you next time.